The next speaker is Dr. Sayantan from the SCM department. He has done his master's and PhD from IISc Bangalore and worked in the James Franck Institute in the University of Chicago as a postdoc. And his research interests are biopolymer-based programmable materials and shear thickening or jamming transitions. So let's welcome Dr. Sayantan to the podium.
Thanks, Rahul. So I'm very happy to be part of this present our work as a part of Platinum Jubilee celebration of RRI. Good morning. So today I'll be telling you about relaxation in jammed dense suspension. So in recent years there is a lot of interest in designing materials whose property can be tuned very widely depending on external cues like electric, magnetic field, force, pH, etc. And such change in material property is rapid, controlled and reversible changes. So these materials in some sense have the ability to adapt to the changing environment. So these materials are called smart materials, and since these materials are not very usual, usually their designing such material is very challenging. So I'll give you one example of a simpler system, at least simple to make, that show similar kind of force adaptability. Okay, so one aspect, so it behaves like a smart material. So you take a liquid like water or oil and put some solid particles. So only condition is you put at very high volume fraction, so almost equal amount of liquid and equal amount of particle, and mix them together. So this mixture, this is called a dense suspension. So just to illustrate what I meant, so this white colored substance here, it is a dense suspension of cornstarch in water. Again the particle volume fraction is very high, like as mentioning. So it is kept in a big bucket. Okay. Now it is like a liquid, the consistency is almost like a paint. Okay. So now if you drop a very heavy object like a 5 kilogram bowling ball, you see a very amazing effect that instead of creating a splash that you would have expected, the heavy ball is bouncing off the surface. So as if the impact force is transforming the suspension into a solid, but if you leave it like this, eventually the ball will sink. Okay. So the same principle you can see, like there are many YouTube videos using same principle. People can actually run across a pool of similar fluid without sinking if they run fast. Okay. So now when I joined as a postdoc, so this kind of work was very popular. So we used to watch a lot of YouTube videos, lot of motivation came from. So actually this is the same phenomena that this guy was running across the pool of cornstarch, but what caught my attention was the later part of video that nobody paid a lot of attention. So he stopped and he demonstrated that you sink inside, but you can see that he had difficult time in getting out also, like it is not very easy to get out. So turns out he got caught in the fluid. So it turns out that this compressive force, like I mentioned, is not a requirement for this striking response. So it can work for extension also. That's why, like when you are trying to come out, you are getting caught. So we studied this system in a more controlled fashion in the lab. You can see that like there is a solid like transformation under extension also, like I mentioned, and doing using some non-optical imaging method like ultrasound and X-ray imaging, we demonstrated that all these phenomena basically why this compression and extension is same. Basically these are phenomena related to shear induced jamming. Okay, so whether you are doing compressive force or extension of the system, you have like inside the suspension this is. So you have high boundary shear component that is jamming this system, and we showed it more decisively So you don't need any compression or extension. So same substance we kept in a beaker this big, and then you have a inner cylinder which can spin very fast, and in the process it creates, it applies some shear on the suspension, and you can see that the shear transforms this suspension into a solid, and like it can support a steel ball bearing, but if you stop shearing, the bearing, the ball sinks basically. So it is a totally reversible phenomenon. So the striking property, so actually that is a good question. So what happens is, it's a, like, once it transforms into a solid, so there is no steady flow possible. So actually, like, there is a slippage at the boundary, but this slippage is not very simple, because see, if it slips and some detachment happens, then it is no longer applying any shear. So immediately there will be some local fluidization, and again contact will build up. Okay, so that's how that solid-like state is maintained. On and off, but those time scales are quite fast actually, even what we are probing. So yeah. Okay, so such striking property, because of such striking property, these systems are being used as a, in designing smart self-adjusting, flexible, shock-absorbing materials basically. So this is a demonstration. So you take a fabric that people use for this, having this bullet or stab proof vest. Now actually, if you take few layers of it, like, and under very high impact or like some sharp object, if you put, so it can easily penetrate. But if you put treat this fabric with this shear thickening suspension, then it gains toughness. So it is demonstrated here. So see, like, you cannot puncture it any further, and actually it can bounce off bullet. Yeah. Yes. Yes. So actually, see, this liquid, like, these are like almost like a paste, like I mentioned, it is like a paint. Consistency wise, but not under impact, it will solidify. So now you see that there are few layers. Now when you treat those particles, actually I was showing you for constructs, but in this case the particles are little smaller. Those are nanoparticle, silica nanoparticle in PEG. So those particles actually get inside the fabric. So you can have that fabric and you put it inside some cover, and then it will stay as it is, because it is a non-evaporating solvent. It will not come out actually, because it's almost like a paste, and if you treat, means you dip it into a shear thickening liquid and you pass it through some roller, and that actually compresses all the particles inside the fabric. Thickened liquid, exactly. So now, and another thing I would like to point out that, see, this flexibility is not lost. This is very important, because you can argue that why not a steel plate, because this while stabbing, like you can see, if I can, that, see, it is still a flexible fabric actually. That is the main interest, technological interest. And here also another demonstration that like it is deflecting a hunting arrow. It has like lot of punch actually, although it is an arrow, it can penetrate like even thick armor. Okay, and there are many potential applications. Some of them are we are exploring currently. So this is summarized in this recent review. In automobile industry, stabilizing lithium-ion batteries, space technology, and preventing sports injury from impact. Yes. Yes, so actually shear thickening, it goes back, that increase in viscosity, it goes back like several decades basically. But now this volume fraction dependent effect, that it can actually go to a solid like jam state, and characterization of these, those have been done mostly over next decade or so. So it has been
so the effect of an armor, for example, old-fashioned armor would be to actually resist such things.
Yes.
But can this do similar things with
Yeah.
lower pressure, but high impact kind of, yeah.
Yeah, so actually so what has been found, like what Sadiq was asking, these are all very recent knowledge that these effects are triggered by stress in the system. So now when you are telling that, so eventually like you are worried about that you require high velocity, but it boils down to how much stress you are applying. So even slow velocity, but if your impact is significant, so that stress is high enough, so you can get this jamming. And I'll come to the later part, because all these things are good questions. So how do you know that, okay, so the amount of impact is like this much, so how do you tune your system? So those things people have not explored before actually. So what are the handle to tune the properties? So exactly what you are asking. So actually microscopic mechanism for this striking effect is very poorly understood, and it is a very active area of research. So the questions which are also very important, like Sumati asked for various application, what sets the upper limit of stress response after perturbation, how quickly the jammed state is reached, how quickly the state relax, and so on. So here I would like to address some of these questions. So actually we are not the first one who are studying these relaxation dynamics in these systems. There are very few recent studies, and all these studies they report a complex non-exponential relaxation in this system, like many which is not surprising for dense system. But in our study we would like to understand some of the microscopic properties that is leading to such relaxation. So I just want to give a brief introduction about like how do you study this system in the lab. So we use some technique called shear rheology. So basically the idea is simple. So the same way we characterize also properties of liquid and all. So you have two plates and you keep the liquid in between the two plates. So here the gap is very high. Actually you keep the gap quite small. If you use a plate geometry, so that surface tension can hold the liquid. So this plate area is A and the separation is D. So now you apply a force, shear force, and in the steady state it creates a velocity V. So then you can define two parameters. This shear stress is force divided by area, and shear rate or shear strain rate is V divided velocity divided by the gap. So even for very small velocity you can get a large strain actually. But like for example if you make the gap twice, then you have to see the same effect, you have to increase the velocity twice like that. Okay. So the ratio is that okay. So the ratio of these two quantities are the viscosity. So you know that viscosity of water is less compared to viscosity of oil or honey, because those are very sluggish. Okay, but importantly the viscosity for all these material, no matter whether it is high or low, it is independent of applied stress. That is very important. So no matter for this measurement how much stress I am applying, that doesn't come into picture, because this ratio is constant. Obviously I am talking about low Reynolds number like turbulence, that is a totally different story. But now what happens if we take such a liquid and put a few particles in these? So at very small volume fraction, actually this problem was studied by Einstein more than 100 years back. So for low volume fraction you put a very small amount of particle. So Einstein came up with an expression that it still remains Newtonian, because viscosity doesn't depend on any stress, but actually the viscosity gets modified slightly from the solvent viscosity by this factor. And phi it is valid only for low volume fraction. So you can see so phi values may be 0.5, 0.05 or something. So it's a small correction, but it's very accurate. Okay, and you can have higher order terms also to go to higher volume fraction. But I'll talk about a regime which is completely out of this capability of this kind of theory. This is the close to jamming, like you put so much particle, like that is our interest. So as you make the system flow, the particles are now interacting strongly with lubrication hydrodynamics or contact forces, and the system becomes completely non-Newtonian, where the viscosity is no longer constant, but it depends on the stress. So this is a typical viscosity versus stress curve for a dense suspension that we studied in the lab. You can see that for small value of volume fraction, it is sort of Newtonian. If you go down further, like you can see pure Newtonian behavior, but as you increase phi, you can see that it becomes highly stress dependent, and this is a log scale. So particularly at high stress values, you can see the viscosity increases by orders of magnitude actually. Yes. No, it is actually independent of the size, because see, that's the formula, the volume fraction comes. So if you put bigger particle, so then only few particle will be enough, but to get same volume fraction you need like okay, so that's okay. So see, there is a, so this volume fraction is 5% or so. Yes. So that's a good question. So see, these volume fraction, it is not the volume fraction of the system, but the, because you have a pure liquid that is molecular. Okay, so that doesn't much bigger than the solvent, but it can be Brownian or non-Brownian as long as they are not interacting. Okay, these are solute particle, colloidal particle or granular particle. Okay, so now this steady state picture, like how do we understand? So yes. They can be polydispersed actually.
And still the same volume fraction argument holds?
Yes.
Okay, fine.
Yes. Yeah, because many of these system, although like in our case the system we are studying, the polydispersity is not much, but this is equally valid for polydispersed system, but there can be some small correction, but overall broadly the formulation works basically, because cornstarch for example, it has a very wide distribution, like it's a totally amorphous system. So 2.5 actually it came from the Einstein's derivation actually. So no, it was some geometric argument, I can't remember fully, because the next term if you consider, that was given by Batchelor and all, so that was like some 6 point something phi square, like numerical factors actually. And it works because see, there like the factor, particularly that Batchelor's factor, like they say that it can vary slightly to fit different systems and all, but it is a kind of motivated by describing the experimental observation. Okay, so how do we understand the property, steady state properties of this system? Like Sadrik asked sometimes back that, see, shear thickening was studied long back. Now, people had some idea that, okay, so these might be some hydrodynamic picture was there for shear thickening, but it was not adequate, that people ignored for a long time. Those models were giving very mild increase in viscosity. Like I showed in the earlier slide, the viscosity increases by a factor of even 2 orders of magnitude. So no model could capture that kind of increase. So then in 2013, in this PRL paper, this Sato, Roman, Mari, and so they actually considered this combination of hydrodynamic and contact picture that can actually give strong shear thickening. And their model was the following, basically the essence of the model. So actually, like in a well dispersed system, all the contacts are lubricated. So now when you apply force, because of this motion, all these real system, like they are frictional. So some of the lubricated contacts transform into stronger frictional contact, and eventually with very high force, these frictional contacts span the entire system. So it gets very well connected and you get a solid like state. As you remove the force, like it will transform into the liquid like state, and next year there is a model by Wyart-Cates and Matthew Wyart. So they actually showed which works for a wide range of system, that how this fraction of frictional contact like gives is related to this jamming parameter and increases viscosity. Okay, but in none of these models there is information about this dynamics of contact formation or the relaxation of the contact. Okay, so we study the transient relaxation of dense suspension formed by polystyrene particles dispersed in PEG. So we synthesize the particles in our lab. So these are weakly Brownian particles, so 2.6, 2.7 micron, and the polydispersity is not much, within 10%. So now this is the experimental schematic. So what we do, contrary to steady state measurement, because I showed you that all these interesting part is under sudden impact transformation into solid and all. So we apply a sudden perturbation, so a sudden perturbation to the system, and we study how the stress relax in the system. So we apply a step strain deformation and study the stress response. So now what is the result? So we apply step strain of various magnitude and we plot stress in kilopascal as a function of time. So you see that as you increase the step height, the peak stress increase and the relaxation happens, and these are strongly non-exponential relaxation. So we could feed the this curve using this kind of expression that has been also found in simulation, but there is no a priori reason that why there is no theory that is telling that this should be the functional form. It was found that it just fits. So there is a power law multiplied by a stress exponential relaxation, and it fits all the curve fairly well. But now, yes.
If I can understand, just what I mean, I know you're using these phrases. A lot of people understand, but what do you mean exactly by transient stress relaxation?
Okay.
Because you said you, yeah. So if you could just explain that.
Yes, yes, yeah, thanks. So actually, see what I mentioned before, that when we talk about that measuring viscosity of water, oil, or any non-Newtonian fluid, so previous measurements are showing that is more or less known. So those are steady state measurement. What you do, you apply some force and allow the system to attain a steady state, because as soon as you apply the force, there is lot of reorganization is going on in the system. So immediately that that flow profile that you get, that velocity and shear profile, it will not get established. Okay, but this transient relaxation we are doing, so that is a steady state measurement, and all these models are capturing steady state shear thickening. But now this impact or stabbing or this thing, like it is not that it is driving the system into waves, these are like happening over milliseconds only. So to simulate that, we are also limited by the instrumental capability, that although we would like to apply a perfect step, but it turns out that it takes around 50 milliseconds for our instrument to reach the desired stress, actually, the step height. Okay, so that is kind of, but within that we are not allowing the system reaching a steady state, and there are some differences. So that is the difference, basically. Is it clear? So actually this is the schematic. So okay, I will show you the, so actually it is not a plane geometry, it is a plate basically. So what we do, we suppose we want to apply some strain, so we suddenly give a rotation, but that rotation like it suddenly increases and then stops, and then that perturbation, it transiently solidifies the system, and how the solid like state relax as we hold the strain there. So that is the experiment actually. Yes. Okay. I see. Okay. So alpha value is close to 0.5 and beta, because the simulation paper that I was telling you, that beta value they reported is 1. In their case it's a just exponential relaxation. But in our case we observed many cases it is 1, but there are few cases it is 2 or 3. It is more actually. That's what if I remember correctly, Sachidanand. So most of the cases we found close to 1, right? Between 1 to 2. Yeah, but see, that depends on, for example, if you go for this 90% strain, that power law regime like extends up to here. So yeah, but exponential is also not very long, because overall relaxation is quite fast. It happens like within entire system relaxes like within a few seconds. Okay. Yes.
That is something that has been established for ballistic rearrangements of particles, which is what you have, right?
Yeah.
I mean, you do see plastic deformation,
Right.
things like that. So yeah. So see, for the lower strains, do you really need that fitting function? I mean, also because the range is very narrow.
No, see, the thing is,
Fitting parameters.
yeah. No, actually it is true that if your strain value is extremely small, because we are considering the stress value, it is not very small actually, it is approaching almost 1 kilopascal. So now we wanted some general functional form, because what happens is, like if you take any specific curve, one kind of function, for example, like it fits fairly well. But how do we know, like we pondered over it for some time. So finally what we thought that maybe we should consider a function that gives best fit for a range of strain values actually. So that's why, like without changing the functional form, we are trying to fit all these for all strain value, and that is sort of generalizes this. So that was the motivation. Okay. So now, so these are all continuous relaxation, but if you increase the strain value further, what we found that the peak stress increase and there is this power law regime, but there is a sudden drop in strain, and then the relaxation continues basically, and this is a log scale. So this strain drop is stress drop is very significant. So you can see that it is almost dropping from 20 kilopascal to almost like 20 kilopascal to 3 kilopascal. So it's one order drop. So if I plot in linear scale, actually for these curve, these relaxation will be like the entire thing almost. Okay. So low peak stress, the relaxation is continuous. High peak stress, the discontinuous stress drop happens.
That drop happens at a typical time scale.
Exactly. Yes. Yeah. So that is the next. Yes. So that is the next slide. So actually, like this is the same plot. I am plotting the discontinuous ones separately. So now we define two time scale basically, like what Supurna was pointing out. So this up to this discontinuous drop, we call it a fast time, and where the stress drops in the next step to a insignificant value, we call it a slow relaxation time. So and the nature of the exact nature of the curve actually depends slightly on the volume fraction, but overall like this we followed this protocol. And what Sumati was asking earlier, that what is meant by transient. So here you can see that we plot the steps, and we would like to have a very sharp step, but you can see that the strain actually reaches to the desired value after almost like 50 milliseconds. So that's why we define the fast relaxation time from that time actually. Although it will not make a difference because these values are very small, but in our case we define when the strain has reached the desired value, and there is some interesting normal force response also that I will skip for the moment. Yeah. Yes.
So
So where the continuous relaxation is there. Yeah. So that no, actually, see this prefactor you can collapse, the peak you can match, but for example, this part you have to also rescale the time somehow. That you have to rescale. So that we haven't tried actually. Yes. From the look of it, actually, I don't think like it will work very well because particularly for this smaller one, the power law regime is very short. But close to just below this discontinuous one, the power law becomes very prominent. That can, yeah, unless you do that time rescaling, yeah, that is hard to tell. Yeah, I agree. Yes. So this normal force is positive. Actually, one thing I'd like to point out. So how much time do we have? Okay. So see, this normal force is positive. So it is pushing the plates apart. But actually, like you can see one interesting feature that when the shear stress is high, normal stress is not very high. And when the shear stress drops, the normal force builds up. So this is in contrast with the steady state rheological result for this system, where the for these volume fractions, the normal stress and shear stress goes hand in hand actually, where the normal shear stress increase, normal stress also increases for this volume fraction that we are considering. Okay, so here there is some decoupling between shear stress and normal stress, so that is interesting. Okay. So to understand this complex relaxation, so this is the actual experimental setup. I was telling that you sandwich the sample between the two plates. This is how it is done, and you apply a counter rotation to apply shear. Then these particles are opaque. We cannot see inside the system. So you illuminate the boundary with a LED light source and image it with a camera. So this is how the setup looks like. You put the sample between the plates and bring down further. The gap between the plate is 0.5 millimeter, very small. Okay, so this kind of setup is motivated by earlier observation. What happens is if you have dense suspension, dense granular suspension confined between two plates, these particles are very big actually, 100 micron particle and all. So what happens, you can see that if you look at the interface, so this is your dense suspension confined between these two plates, and this is air. So as you shear the system, the particles dynamically protrude out in and out of the interface actually. So this is visible in the movie that as you shear, the particles actually make this deformation of the interface. So this dilation, it is well known that if you shear granular system, so the whole pack swells, but here this dilation has to compare with compete with the liquid air surface tension. So surface tension force is trying to keep the particles inside. So in essence, like you are expecting some sort of change in surface texture. So that was the basis for our imaging setup. So let's see what we get. So this is the top plate and bottom plate, and so we apply a sudden shear. You see that there are several bright spots which immediately disappears. And then there is some evolution of the surface, like it looked like rough and then it goes like goes back to initial fluid-like state. So these bright spots we term as plastic center. Why? Because like although we are not going to this regime in this talk, that if you apply very high strain where the sample fails, actually you see that those bright spots actually line up like this, and they eventually can create a fracture that we are studying in more detail using high speed imaging. Okay, so now in essence that this accumulation of such bright spots triggers plasticity and eventual material failure. So individual bright spot, we think that it is related to localized plasticity in the system. Yes, yes. Okay, so now let's take a closer look. So this is the same kind of imaging but with a greater magnification. So you see that again sorry, let me just go back for a second. So here we are plotting the stress response versus time. Sorry, this is no longer kilopascal, this is Pascal now. Anyway, so what you are going to see, like as we apply shear for high value of from high stress value, how it relaxes basically. So and the simultaneous imaging of the system with a higher resolution. So you can see again these bright spots are formed, but you see the other particles protrusion also now. So once this after this first step the bright spots disappears, but then in the second step the other bright spots disappear. So let me play it once more. Okay. So what you are supposed to see that as we apply strain, there are you can see all the particles basically protruding out. Some of them are very bright, that we are termed as a plastic center. So during this first relaxation process, the brightest spots, those will disappear, and eventually the slow relaxation will take place. So that we don't fully understand, but our understanding is those bright spots, the particles locally it protrude out much more actually. It is like a defect in the system. So it is scattering more light. So that is what we did actually. So see again, you have bright spots, then those spots relay. Yes, actually that's a very good point. So that is how plasticity is defined usually in glassy and granular system. But the problem is since these particles are opaque, we see only when they dilate, and after that so if you do high speed imaging, probably you can imagine that during that this relaxation process some displacement you can see, but actually the particle, their tendency is as that stress drops, it goes inside the bulk, so you cannot track them any longer. So probably you can index match the particle and do some I think better imaging to track that, but that is how plasticity, but we are defining plasticity just from a like taking that concept that accumulation of many of these bright spots leads to material failure, so individually they must be local failure. So that is our conclusion. But actually more rigorously one should do this.
Can I just make a speculation about the mechanism and you tell me how wrong I am?
Yes.
So you have some 50% volume of these beads. Okay. Now what you're doing is when you drive it, there's tremendous friction which is generated. Because of the friction in the space where the friction is generated, the particle size expands because it has very little fluid too, and that causes jamming. Okay, that causes additional jamming as the temperature stops. I mean, as the temperature in that local portion of stress re-equilibrates because it is kind of distributes in the bulk, the particles restore back to size and the jamming this thing goes away. I don't know.
No, so actually it is not a temperature induced effect, because see, like we studied this like using ultrasound, like you can see like if the volume fraction of the particle changes. So you can do that actually. It is true that there are thermoresponsive particle where the increase in temperature will make the particles expand. But in this case, it can be shown that the local volume fraction remains constant. It is just a geometric arrangement. These are hard sphere basically. Yeah.
What about the idea that they are picking up the friction? I mean, you can have
Yeah.
non-uniform heating up with certain.
Yeah, but only thing is this. See, this temperature like the coefficient of expansion for these particle, like at least like overall system.
It's not an expansion. Something that the fact that you have a higher temperature
No. No, usually not, because these are scattering from the rough surface, so some spectroscopic properties can depend on a very sensitive parameter. But like even for granular system, like if you have very really big particle where like even let's say sand particle or something, these effect you can see still. Okay, yeah, so these are interesting.
So the results that you get, do you have the little simulations which try and replicate them?
No, not yet actually. Like I mentioned, the simulation gives some insight about like how this jamming comes, but actually there are no reports about like, there are, I mean, very recently there are some study, but those are not actual, like it is based on various assumptions and all, like they don't show exactly how the contacts relax or something. So what they do, there are some experimental studies, so they speculate various form that okay maybe particles can get compressed or something. So they try to match some of the relaxation, but this discontinuous relaxation and all, like it has not been studied in simulation. But we would like someone to study, we cannot do this.
Just one quick question.
Yeah.
So because you have positive normal stresses and therefore frictional contacts are dominating.
Yes.
Do you see any evidence of force chains?
Yeah, so force chain mechanism actually in dense suspension it has not been seen because of presence of liquid. Like in dry granular system, if you do a imaging between cross polarizer, Bob Barringer and all they showed. So now in simulation they see force chains like I showed, those are actual simulation result. But experimentally in dense suspension force chains have not been seen. But recently like I did some work where like force chains are difficult to see with Sarika and Sood. So they are like we can use very dilute system of carbon nanotube where you can see this the contact you can map out, and if you reverse the contact breaks and all. But actually we don't have anything that can measure the stress in the system. Now we'd like to have if it is possible. Yeah. Yes. Sorry. So actually like you have a particle between these two plates, the dense suspension, particle and liquid. So now from the edge you get some interface, right? Now you shine some light on the interface and then focus a camera, see how the texture looks like basically.
Yeah, so let's say that we don't shine any light and then we put the strain on. Can we still see the plastic centers?
No, you need some scattering actually, unless you have some other detection like are you talking about any infrared emission?
Yes, that's
or
what I'm
something?
talking about. Because let's imagine.
Okay.
Because maybe I'm changing the magnitude of scale, but as the strain pulls on it, if I go to molecular scale, maybe the change in emission states of those electrons changes, which changes the states, which might be in a way cause for the plastic center as well.
Yeah, that's a good suggestion actually, because see, like we don't see anything optically, but if you put a infrared sensor or something, and one can see like if there is any signature in infrared, basically outside visible range. Yeah, that's a good point. Thanks. And maybe that is related to what Sadiq was asking, that local temperature change and all. Yeah, we'll think about it. Huh? Oh, okay. Sorry. Okay, I'll just rush over a little bit. So now what we did, we actually have the bright spot, very bright spot that we call plastic center, and some region where you can see protruding particle, but it is not so bright. So then you, what we do, we consider some area around this and we observe intensity as a function of time, because intensity is changing as the system relaxes. So you see that these bright spots, like there is two-step relaxation actually. There is a fast relaxation and a slow relaxation, and then it goes back. Whereas for the region where there is no very bright, there is no bright spot as such, but you can still see the particle. So this is sort of intermediate brightness that so that you can see the particle, but it is not like a bare interface, unsheared interface. So there you just get a single step relaxation. We did this experiment over many such spots, and we plotted the distribution. We defined this first step, the time scale corresponds to this as a plastic center relaxation time, and the second step as dilation relaxation time, and we clearly see that there is some distribution, but there is a clear separation of time scale in these two cases. Okay. So we did another thing. So during the relaxation, so we considered two consecutive images of the interface, which are separated by basically the time of our resolution. Time resolution, which is 16 millisecond. So we consider two consecutive images taken at time t and t plus delta t. Delta t is 16 millisecond. Now we take a image difference. Why? What we are expecting? Because see, if there is no reorganization, that image difference will give a completely black image, right? They are absolutely identical. But if some local rearrangement takes place, you should get some bright spots if you plot the magnitude in the difference image. So same thing we did this slower relaxation process. So this is during the first step relaxation. We also did the same thing for slower relaxation. Sorry. Okay, and this time difference is again same. So you see that for fast relaxation, if you take difference image, you get very isolated bright spots. Okay, so so we concluded that localized particle reorganization is responsible for this fast relaxation, whereas if you take the same similar image difference in the slow relaxation case, you see that there is distribution of bright spots all over the system, that the reorganization is taking place over the entire system. So system spanning particle reorganization gives dilation relaxation. So then we plotted 4 time scales, this plastic center relaxation time like obtained from imaging, and dilation relaxation time again from the imaging like I pointed out. So this is the first step and slower step, and we also plotted the fast and slow relaxation time from our stress measurement, that bulk rheology measurement. So now you see that this plastic center relaxation time matches very well with fast relaxation time for all volume fraction, and likewise the dilation relaxation times matches with the slow relaxation of the system. Okay. So that's so we concluded that this fast relaxation is due to localized plasticity and slow relaxation is system spanning reorganization. Now to test it further, what we did, we varied the solvent viscosity. We put the particle with same volume fraction in a solvent with different viscosity. So you see that this fast relaxation, the fast relaxation time almost is independent of the solvent viscosity, whereas slow relaxation time depends on the solvent viscosity, and if you increase the viscosity, the slow relaxation time increase. So together with these two, this again the same curve volume fraction dependent. So it matches our kind of assumption that slow relaxation times increases with increase in solvent viscosity, because it is a system spanning reorganization. So if you have more dissipation in the system, it will affect, but fast relaxation remains unaffected because this is depend on probably just the neighborhood of the particle or defect created. So it is insensitive to that system spanning parameter. So this I will skip. So actually what we got, so this is again going back to the steady state shear jamming. So here the prediction from the Wyart-Cates model that this is the shear jam region in the steady state. So we just put the nature of relaxation on the steady state curve just to see there is any correlation or not, because I told you this transient relaxation there is no theory basically. So just to get any, if there is any connection. So interestingly, you see that in this green region, this above this line, that is the steady state shear jam region, if we do this transient relaxation measurement, you get first of all two region. One is discontinuous region for very high peak stress value where you get 2-step relaxation, and this is the continuous relaxation given by that Paul law cut off by stressed exponential function. However, if you just go out of this shear jamming steady state boundary, looks like you can fit everything quite well with a simple stressed exponential. So looks like that there is a connection between the steady state prediction and the nature of relaxation you get, but there is no theory. So these are the conclusion. We show two distinct relaxation in shear jam dense suspension. Localized plastic events gives fast relaxation, system spanning dilation gives slow relaxation, and correlation between transient and steady state is like, we found some interesting connection, but beyond that nothing much is known. So this is just the future direction. So actually this shear jam state from simulation, like if we zoom on to a local region, like you have these contacts, you can see. So now based on some recent evidence, we think that we can discuss, actually if anyone is interested, that with increasing strain, these force chains actually it develops local buckling, and those are like plastic center. There are some evidence for that. But these plastic centers that are like highly directional also. So in this picture you can see that we start with few plastic center, bright spots. Now if you go shear the system further in the same direction, the number of such bright spot increase, that you develop more plasticity. Whereas you start from some plastic center and you go in the opposite direction, the plastic center immediately disappears. So based on this, basically we are trying to understand what is the character of plasticity that is unknown. What Sanjeev pointed out, that in simulation from displacement of the particle, that they have, like in the defect site you have more particle displacement, but we need to understand. And second thing is, like see, this non-exponential multi-step relaxation has also been observed in glassy systems, okay, but there the relaxation times are very, very slow, like it is many orders of magnitude slower than these systems. So now we observe this for very fast time scale. Now is there a connection between, because both are dense disordered systems, so is there a connection between these two? That is a kind of open question that I would like to address. So this is the acknowledgement. So all the experiments are done by Sachidanand, and we thank Jatindran for SEM imaging. So these are my current lab members, and we thank RRI and SERV for financial support. Thank you. And if you are interested, like this paper got published recently, so particularly that supplementary information, lot of technical details are there that I have been skipping throughout my talk, so you can take a look. Sorry for going over time.
That was a great talk. Let's all thank. Okay, we can have one or two questions.
Sayantan, in these relaxation plots, you have, when you start from a very high point, it comes down and then, so there is crossover between two curves. So does
Yes.
that mean from the point where they crossover, the evolution is not identical, it has a kind of a memory of how it arrived there?
Yes, exactly.
How
That's
would
a.
one explain that?
So you are, so for example here, see this one you are talking about, right? Yes. So actually what is interesting, that is a very nice point, that see we have in the continuous relaxation we have this power law decay and this stressed exponential decay, okay. So looks like that this discontinuous regime, these two functional form gets decoupled basically. So what happens is this power law gets separated. So initial part is still a power law because it's a log scale, but this second part actually I haven't shown fitting here, so you can fit it very well just by a stressed exponential relaxation. Yeah, it is true that actually like this state of the system after this jump, it is no longer same as continuous relaxation curve, because it is not surprising because you have very high stress in the system. So after that jump, that sudden release, it will create more localized arrangement. So we also don't expect that these two curves will be identical after such a large release of stress.
And one bad question, how would you rule out any instrumental effect in this? Like if you probably try with different concentration or different solvent, it should not show anything at this time scale.
So
There is
actually,
possibility of any instrumental effect at 30 millisecond or
no, so actually these type of discontinuous relaxation, we changed various we considered various other particles also, like bigger polystyrene particles or silica particles and all. So looks like that this time scale can go vary slightly, and this slow relaxation times, like it gives a bigger effect.
so that gives confidence. It's
Yes,
like
and also from the imaging that we can see the structure of the sample, and they correlate with this kind of relaxation. So that is our.
Okay, one more question. Yeah. I think after this question, questions can be asked during the break.
Yeah, so just a curiosity question. Have you done these same experiments with by charging the plates? Okay, so my expectation in my foggy way of thinking about this particular problem is that if you kind of put a bias on your shearing plates, okay, which is very easy to do in your this thing, you just have to put some kind of a contact. Would you expect a large, I mean, has anybody done these experiments, and would you expect a significant change with volume fraction, in terms of volume fraction and in terms of the shear thickening and whatnot?
Yeah. No, so actually what you are telling, that is something called electro-rheology. People have studied, but not in these contexts. So what you do, like your particles are basically dielectric particles. So now when you apply a electric field, basically it develops local dipole, and strong enough field, they chain up basically. So what happens is, even without much force, where you are getting low viscosity region, your viscosity jumps even without any applied force basically. So that is, it develops yield stress. So then the dynamics is basically, as you apply force, how the force chain, not force chain, I mean those chained up particles, they basically break and go to the fluidized state. But in the context of these, there is no study. So that is a totally different kind of system. Similar kind you can also see, like if you have very highly charged particle, they are forming some kind of cluster or like some long range interaction, like Ranjini studies Leponite particle. So now there, the system to start with, if your volume fraction is high enough, you start with a yield stress, solid like state itself. Now your shear, instead of solidifying it further, it breaks the solid like state basically. That's an interesting point.
Okay, let's thank Sayantan again for the wonderful talk.